right, by now you're starting to get the hang of how chemical reactions are written, how you balance each one individual compound, then you do the left and the right side. But we have to get you to the point where you can look at what two things are just putting next to each other and you can start to guess, oh yeah, that's right, those are going to break down this kind of direction. So let's look at every kind of reaction here. So for today, you'd be able to predict what the reactions were if you were just given starting materials. For instance, if you have a carbon-hydrogen compound with oxygen, what would you predict that's going to be? Well, oxygen always combines and makes a compound with every element in that compound. So if we were going to write one down, let's write down something like C5H10S plus oxygen. Okay? So what would you guess that product is going to be? It's going to be the same for every time carbon and hydrogen, oxygen compounds, or nitrogen or sulfur compounds react. Every single one of these becomes part of the new compound with oxygen. So I'm going to write this underneath, way over there. We're going to take carbon and oxygen. What does that become? Well, that one should become pretty old hat. C is +4, oxygen is -2, so that's why we know it's +2, CO2. Remember, +4 -2, that's why CO2 ends up becoming that proper at -4 charge, +4 charge. Hydrogen's going to make a compound with oxygen. That's going to become water. And then all the other elements like nitrogen or phosphorus, we're just going to assume they go to O2, something O2, like sulfur dioxide. They do, you know, it's a complex mix. If it's incomplete burning, it might make SO2, S2O3. Something, you know, it may make a weird combination, but we'll always assume it looks like the carbon does, and that's just an easier way to remember it. Like these guys are saying right here, NO2 or SO2, unless there's incomplete combustion. So when you balance this, you're going to just start with the carbons. Leave the oxygen for last because it's spread all over the place. So carbon's going to be the first one. 5 carbons. 5 carbons. 10 hydrogens. So I'm going to need 5 waters. 1 sulfur. 1 sulfur. That looks pretty good. Now the oxygens are the last things to balance. So I've got 2 here. Plus 5, that's 7. Plus 10 more, that's 17. You can't get them out of here otherwise, but let's use that little trick where you cover this up. I have 17 more oxygens on that side, so I'll take 17 halves. Okay, and how do I get rid of this? Get rid of the half by doubling everything. So I'm going to put a 2 in front, get rid of this little guy on the bottom. Come on. No way. There we go. Double this. This becomes 10. I'll just make it big and dark. This becomes 10. This becomes 2. Okay? So that's always going to happen. Anytime you have a carbon, sulfur, nitrogen, whatever compound burning. If it's just a synthesis, it's as easy as just mashing them together and putting their charges up there. So that's combustion. Synthesis, always just going to smash the two together and then just put their charges there, just like I was mentioning up here. So synthesis, that's easy. If you have 2 elements there and there's nothing else you have to guess, just put them together. Decomposition. Now, most of the time, if it's 2 compounds, the binary compounds, easy. Split them down the middle. Don't forget to put, diatomics have to have 2s after them. But there are a few. These rarely have the energy to do this by themselves, but if you put them under heat or you electrolyze them or you shoot them with some light, that might be given the symbol. If you see something like this, HV, or the symbol electric, they will literally break those down. So you just got to learn that these are certain ones that have patterns. So like, for instance, sodium carbonate or potassium hydroxide. Any metal can be the M in this system. And I'm going to take an example of one. Let's take chlorate, and let me take aluminum, for instance. Aluminum chlorate. Chlorate is a -1, so it looks like this. Let's say I heat the crud out of it. Aluminum chlorate is going to break down. Well, here's the chlorate. What sticks with the metal? Chlorine does. That's what this is saying. If you have a chlorate, any metal with a chlorate, the chlorine stays and gives up all the rest of oxygen. So I'm going to get aluminum chloride, which is still +3 -1. So that's going to be AlCl3. And the rest is going to become oxygen. But we got to balance the left and right. So each time you do this, you individually balance them. And I got the aluminum balanced with chlorine, oxygen balanced with itself. It's a diatomic. So the last step is I got 1 aluminum, 1 aluminum. 3 chlorines. Don't forget there's 3 in there. That means 3 chlorines. But I've got 9 oxygens, 3 of 3. So that's really 9 halves. We'll do our little trick. Put this over 2. And that'll be balanced. But you don't finish by leaving a half in an equation. So I'm going to erase, I'm going to erase that. All right. So I'm taking the half out of there. I'm going to put a 2 in there and a 2 in there. Okay? So that's how decompositions are predicted. You just throw them apart, except for these ones that are more than 2 elements. Then look at this pattern to help you solve those. All right? I'm going to take these out of here, clear this ink. So the next piece that you're going to work on is single replacements. Now, the key on single replacements is you just have to look at, like if it's a metal and it's competing with another metal, they're like dance partners. There's a guy and a guy cuts in, or a girl cuts in. And so who's going to be the ones that are competing? The 2 metals. So when you have single replacement, whatever you have, you're going to say, oh, I'm getting a metal that's coming in to replace this. Which one should it replace? Let me give you an example. If I took sodium chloride, and I reacted it with potassium metal, okay, I'd say, what should I expect? Well, I come over here. Here's sodium. There's potassium. Which one's stronger? Which one's higher on that list? The higher one gets the partner. Right now, sodium's lower. It has the partner, so sodium gets kicked out. So this will become potassium chloride plus sodium metal that gets booted. Why? Because potassium is higher than sodium. Notice all those are metals. You only compare metals to metals. When would this kind of a transition take place? Well, if I said, let me take chlorine and add that to sodium fluoride. Say, is that reaction going to happen? Well, chlorine is a nonmetal, so it's competing with which of these 2? It's competing with the fluorine. That's the other nonmetal. So fluorine and chlorine. The other reason to think of it is because they're the only 2 in this same column. The same column, chlorine and fluorine. Which one's already higher and stronger? Fluorine. Fluorine's already higher. It's got a partner. It can't be kicked out. So this is a no reaction. Reaction because fluorine is stronger because it's higher in the list. It can't be pulled out by these. You cannot compare, something from this list to that list. Metals compete with metals. When they want to cut in on the dance floor, they're going to kick the other metal out and say, I want to dance with the partner, because they're opposite charge. That's why they're sticking together. Non-metals compete with the other non-metals to stick for the other opposite charged particle. Okay, so this is a no reaction. Sometimes that can occur. That's the single replacement. I'm going to leave the double replacement for the next little lecture, because that one's got 3 rules. You can work on your assignment here as a sheet that I have out for today.